Salam and welcome everyone. Today we're going to be working on the question on the screen that says calculate the molar solubility of methane at 1.0 bar in benzene at 25 degrees Celsius. So the first thing you have to note is that we're told to solve a question from the Atkins Physical Chemistry 11th edition textbook. It is in chapter 5A and it is number 9B. So we're told to find the molar solubility of methane. For those of you who do not know, molar solubility is just another way to say concentration or molar concentration. So, really, what they're asking us to find is the concentration of methane, which is a gas, CH4, okay, at 1.0 bar. So, the gas is at 1.0 bar in benzene. Benzene is going to be the solvent in this case, and we have got methane gas that is in um, benzene, okay, at 1.0 bar. Benzene here being, of course, a liquid and methane being a gas. So there is a mixture in this situation. So we have 1.0 bars. So that means the pressure of methane of CH4 is simply just going to be 1.0 bar. So yeah, so we're now told to calculate this from this. Now you're gonna be wondering, well, they only gave us one question. They only gave us one question to solve, which is the concentration of the molar solubility of methane, and they only gave us one parameter to work with, which is the pressure of the methane. Now you're gonna be wondering, then how do we solve it? Like, what are we doing here? Now, this question just requires us to use something called the Henry's law. And Henry's law is very, very important whenever you're dealing with mixtures that involve gases that are dissolved in liquid. And it just simply explains that. So there are two Henry's law. I'm gonna tell you both. One is in from the textbook, and then the other one is from like an online resource. And then we're gonna look at both of the laws I'm giving critically to determine what law you're actually supposed to use in this question. So Henry's law state that this is the first law. Henry's law states that the vapor pressure of a solute is directly proportional to its mole fraction. In this particular case, the formula that represents this law is just simply the vapor pressure, where B is the solute, is equal to X sub B, which is just the mole fraction, multiplied by K sub B, where B is just the Henry's law constant for the solute in the solvent. So let me just write that down. Here, P sub B is the vapor pressure of solute, okay? Here is the mole fraction of solute. And then here is just simply Henry's law constant for solute. For solute. Now, the second Henry's law is just simply Henry's law states that the partial pressure of a gas above a liquid solution is directly proportional to the solubility of the gas. Solubility of the gas. So they're telling us Henry's law states that the partial pressure of a gas above a liquid solution is directly proportional to the solubility of the gas. So we denote this one here by the formula P sub B is equal to B sub B is equal to K sub B, where B sub B is just simply the partial pressure. So the partial pressure of solute B, it's not equal to here, it's multiplied by. So let me rewrite this formula. So P sub B is equal to B sub B multiplied by K sub B. So of course this is in pink by K sub B. So like I explained. So like I explained, P sub B is partial pressure of solute B. B, right? Sub B is just molality, okay, of solute B. And in this case, the gas is the solute. Okay. So when we keep saying the partial pressure of a gas above a liquid, it's just telling you that the gas is the solute and the liquid is the solvent. So yeah, that's just basically what's going on here. And then K sub B is, of course, Henry's law constant for the gas or for the solute. So Henry's law constant for solute. Now that I've given you what the Henry's law formula is, when you go back to the question where we're told to calculate the molar solubility of methane at 1.0 bar in benzene, we already know methane is a gas, we already know benzene is a liquid. We see that in both questions, what is most likely for us to use is going to be the second law. Because in the second law, we're dealing with keywords such as partial pressure. We know that we're dealing with a gas. We know that we're dealing with a liquid solution, hence the solvent, which is benzene, and the gas methane. We also know that we're dealing with solubility of the gas, just like here it was mentioned, molar solubility. But if you look at the first law, we see that we're dealing with mole fraction. And in this case, we have nothing to tell us what the mole fraction is, neither were we given the mole fraction. So we're most likely going to use this second law. So looking at the second law, in this case, again, like I explained to you, the solute is the gas. We're no longer using the value B, like in the general equation. We're going to start denoting everything in terms of CH4. Yeah, so that's it. So solution, the Henry's law constant for this question will be P sub, not B in this case now, P sub CH4 is equal to B sub CH4 multiplied by K sub CH4. So yeah, so we've got the P sub CH4 to be 1.0 bar. We have got the value, which is a constant for CH4. For those of you who do not know, whenever you're told something is a constant, please remember that if it's a constant value, then it is just one value. So you don't really need to solve it. You just have to look at the resource section of your book or just check it on Google. Just like if they ask you for the gravity, the value for gravity, you're not going to go determine the value for gravity. You already know it's a constant. If they ask you for the Avogadro's constant, you already know you're dealing with 6.022 times 10 to the power of 23 per mole. You already know all these things that are constant value. The gas constant 8.3145. You know speed of light. These constant values don't require you to solve for them. So if you already know an equation or what you're solving for has a constant value, please do not get confused and just use the constant value that you already know. So in this question now, they didn't give us the constant value. And the constant value is just the Henry's law constant for the solute. And so we need to find the Henry's law constant for methane in benzene solution. And looking at the back of this book, the Atkins Physical Chemistry 11th edition textbook, we see that the Henry's law constant for methane gas in benzene solution is just simply 44.4 times 10 to the power of 3 kilopascal kilogram per mole. So that's the unit, kilopascal kilogram per mole. That's basically the unit. So now we have the value for this and we have the value for this, but we do not have the value for the molality, so B sub CH4. So we can just simply calculate that. So we have B sub CH4 is just going to simply be P sub CH4 divided by K sub CH4. So we can just simply substitute. But before we substitute, let's not forget that we have a situation where the value for the unit for pressure in one value is in bar, the other value is in kilopascal, and we need our answer to be in the proper units in order for us to properly solve what we're solving. So I am going to convert 1 bar, okay, 1 bar to whatever the value is in kilopascal. So therefore, 1 bar is equal to 100 kilopascal. This was explained again in chapter 1 of the Atkins Physical Chemistry 11th edition, which is simply how to convert between pressure units, between volume units, as of course, and of course, how to convert from Celsius to Kelvin. So yeah, this is a known value. So we're going to substitute 100 kilopascal instead of 1.0 bar. So therefore, B sub CH4 molality, or the molality value for CH4 will just simply be 100 kilopascal divided by 44.4 times 10 to the power of 3 kilopascal kilogram per mole. So that's it. So of course, we cancel out the kilopascal, cancel out the kilopascal. So B sub CH4 is just simply 100 divided by 44 times 10 to the power of 3 is just 0.002252225. So you now have 1 over kilogram per mole, which is the same thing as mole per kilogram. So 0.002252225 is just simply going to have the unit mole per kilogram. So that's basically the value for the molality. Now, remember how I explained to you that what we're actually supposed to solve for is the concentration. But molar solubility is different from just solubility or molality. In this case, the value for B here is the molality. Okay. But we're asked to find concentration, and concentration is the same thing as molarity. So here we have our answer in mole per kilogram, but the value for molar solubility, the unit is in mole per liter. How do we get from there, mole per kilogram, to mole per liter? You now have to remember that from Gen Chem, again, we see that molality, okay, which is in mole per kilogram, so moles of the solute that you're dealing with divided by the kilogram of the solvent, or the mass in kilogram of the solvent. So we have to go from molality to molar solubility or concentration, or again, you can call it molarity, where the final answer is just going to be in mole per liter. So thinking of what you've learned in Gen Chem before me as your tutor, you have to remember that to go from molality to molarity, you have molarity, okay, is now going to equal, so that's mole per liter, so is going to actually equal to the density of the solvent that you're solving. So the density of the solvent multiplied by the molality. This is Gen Chem stuff, and not all teachers go in detail for this, but it's very important that you study it, because you need it now in a question like this. So molality, which is mole per kilogram. And again, you can also think about this question in a different way. How do you go from mole per liter to mole per kilogram? Remember, density is just simply mass over volume. So we just have to make sure that the density of the solvent is in the units of kilogram per liter, in order for us to be able to make sure we have the mole per liter at the end of the day, because the kilograms will simply cancel out. So all of this will be clear to you now as we keep on doing our solution. So yeah, that's basically what's going on here. The value for molarity is just the density multiplied by the molality. That is it. This is Gen Chem stuff. I know it's not easy because not everyone had the same Gen Chem teacher, so not everybody will go into detail. This is actually something I didn't even remember, but doing this question reminded me of how to go from molarity to molality and vice versa. So let me rewrite this. So B, okay, B sub CH4 is simply the density of benzene, okay, because that's what we're working with, of BENZNE. So benzene multiplied by, the concentration. So writing it in terms of what we actually have in the question, the concentration, okay, so C of CH4, which is what we're solving for, is equal to the density of the solvent, in this case benzene, okay, multiplied by the molality, in this case B, which is what we've already previously solved for. So B sub CH4. So looking at the research section of our textbook, we see that the density of benzene at 25 degrees Celsius, because again, they told us this whole thing is happening at 25 degrees Celsius. If we're in a situation where we're dealing with it happening at 100 degrees Celsius or any other temperature, then the density, of course, is going to change with temperature. So the density of benzene at 25 degrees Celsius, basically at room temperature, is simply going to be, so C sub CH4 is the value is 0.874 kilogram per liter, multiplied by the value of the molality which we solve for. So that would be 0 point multiplied by 0.00225 mole per kilogram. So yeah, that's it. Now, of course, we cancel out the kilogram here, and we cancel out the kilogram here in the denominator. So CH4 would just be multiplying 0.874 by 0.00225. And that would just give you 1.968469 times 10 raised to the power of negative 3 mole per liter. So yeah, that's basically that. Now, this is our answer, but we're chemists and we have to put our work in the proper number of significant figures. So we have to go back to the beginning of our question to see the lowest number of sig figs in the values we're given in the question. So going back up, we see that calculate the molar solubility of methane at 1.0 bar. We're giving our value in 2 sig figs. So our final answer has to be in 2 sig figs. So the molarity or the molar solubility of methane at 1.0 bar in benzene at 25 degrees Celsius is simply going to be 2.0 times 10 raised to the power of negative 3 mole per liter. And this is basically the answer to this question. There are other questions like this that I'm going to solve from the Atkins Physical Chemistry 11th edition. There are actually like 3 or 4 other questions that look like this. I'm going to solve it. And I think the more I do them and the more you watch them, the easier it's going to be able to like handle questions like this on your own and just basically do your very best. So, yeah, if you have any questions, suggestions, or concerns, make sure you put it in the comment section. And if you would want me to be your personal tutor, I help students succeed in all your STEM related courses, whether you're in middle school, high school, or university, to become the best version of themselves in academia by my way of tutoring and mentorship. So I tutor students a range of STEM courses from organic chemistry to physical chemistry to all the calculus that you have to algebra to differential equations. So if you do want to book any of my services, email me at shahavitutoring@gmail.com. I wish you guys all the very best. Assalamu alaikum wa rahmatullahi wa barakatuh.